Hi everyone, Architecture and Operating Systems. We are in week 15, and in this week, I'm going to talk about the fetch execute cycle. I hope by this time you have watched and read the materials for week 13 and 14 for the last 2 weeks, because they are quite correlated with what we discussed in these 2 weeks. So, what we discussed last week was introducing and talking more about IAS machine and the Van Neumann architecture. As you see that here, we've got input output device, we've got main memory and ALU, and also the control units. These two together is called central processing unit or CPU. Also, we discussed the registers, the temporary storage that is used to send and receive the data, store them and send the receive the data to one of these four key components of the computer. We've got MBR, which is the memory buffer register here between ALU, main memory, input output, and also the control unit. We've got MAR here, which specifies the address in instruction. We've got IR, which is the instruction register. We've got the buffer for that, which is called instruction buffer register, which for this machine was dedicated for the write instruction on the 40 bits instruction. We've got program counter, which actually holds the instruction number and the next instruction that should be fetched and executed. And also AC and MQ, which holds the output of the circuit and the arithmetic logic unit that we have. They are very important, and I'm going to show you how to use them in this lecture. Also, we discuss about programming hardware and programming in software. In the hardware, we've got the um, circuit, and manually we've got to create a circuit, then load it with the data and get the result. But in the software, programming software, instruction actually are stored as a code, and then they are interpreted and send the signal to the general purpose arithmetic and logic unit that we have, and then it's loaded by the data and the results are released. So this is different and with programming hardware, and Van Neumann architecture IAS machine works based on programming in software, because we both store instruction and data on the main memory. Now, let's talk about the main computer function. Whatever computer does is based on a program that it's being executed. And computer is about execution of a program. Program is set of instructions. Any program that you write, very simple one, get x, get y, z equal x plus y, they are compiled and stored on the memory as instructions. And line by line of these instructions are fetched from the memory and executed, and then you will see the summation of two numbers. So program is set of instructions, and the main purpose of the machine is to execute the program. Processor execute the instruction in two ways, in two cycles. One of them is reading the instruction, we call them fetch, and the other one is perform the instruction, which is called execute. So fetch execute cycles, in these two cycles, the computer repeatedly read from the memory instruction and perform them. Reading and performing, fetching or executing, is a loop that happens inside the machine repeatedly, and the output is what we see as the performance of the computer. So program execution, when you run the program, when you write a code in Java, for example, when you execute the code, this is what happens, repeating fetch and execute. The fetch execute cycle, as you see here, when you press start, let me use that. When you press start, instructions are read and then executed, and this loop goes again and again until we break the code You write a line, a code of breaking the code, returning a value, stopping that, whatever, or interruption. For example, you're running a program, you're watching a video, and suddenly you run another program. So it stops the um, uh, running the video and execute another program. So when you interrupt that, interrupt is a very important topic in this area, but I'll leave it for you if you're interested to read about that. At the end, I will introduce a book that actually you can read about this, which is out of the scope of our study here. So what is important? We start and finish. Meanwhile, fetch execute happens. So what happens in fetch execute cycle? Again, we use all these registers that we discussed. We use this main memory. I told you last week that the main memory is addressable, as you see here. So we have instruction and data stored on the main memory. We've got registers and we've got input output module, and definitely a control unit, which is here, actually helps to run these fetch and execute cycles. So let's see how it works. Instruction fetch and execute. Look, guys, this is hypothetical machine that I'm going to explain you, and I'm giving an example. This is just show what happens. Definitely in our these days machines, the way that it's performed and executed is totally different, but the fundamentals are the same. The architecture is the same. So this is the hypothetical machine. This is not exactly what happens on our machines, but it gives us a very good picture of what happens inside our machine. So in this example, we've got 3 cycles of fetch execute, and what we want to do, we want to add 2 numbers and see what happens in the machine using all these registered different components of the computer architecture. We want to add 2 and 3, 2 plus 3, and save the results in the memory. So the machine should get the first number 2, second number 3, add them together, store the results on the memory. We use single data register. It means that we use only one word for each register. In these days machines and actually today's machines, we use actually multiple line of memory, let's say, for the register. The machine that we are going to use has got 16 words, and again, this is based on IAS machine, but in IAS we've got 40 bits. Here I'm going to use 60 bits just to show you what happens. And from this 40 bits word, 4 bits is for opcode, and definitely the rest is for the addresses. So how many words, how many opcodes that we can have? If you assign 4 bits to the opcode, 2 to the power 4, which is 16, is the number of the operations that we can have in this hypothetical machine. We can load, we can store, we can add, we can subtract, and some others, up to 16, because we've got 4 bits for opcode. How many words for the address? The rest is for addresses. 4 bits out of, if you take away 4 from 16, 12 bits remains for the addresses. So 2 to the power 12 should be the memory size for this hypothetical machine. So it's very important to understand the bits for opcode and the bits for addresses. Program counter is set to 300. It means that in the memory, the location, which is 300, is the start of reading from memory. So we start reading from position 300. I'll show you how it is. And you should have an opcode list that I'll show you in a second. So look, guys, we've got an opcode list, the codes that our computer should understand. I said that we've got 4 bits for opcodes. 001, for example, is loading data. Load AC from memory. It means that we load AC, the accumulator, from the main memory, whatever it is in the memory. Store AC to the memory. It means that you want to write on the memory is 2, which is in binary form is 0010. And Add to AC is if you want to add number, there is a number on AC and you want to add a number to that, it's 5, which is 0, 1, 0, 1. So as you see here, we've got 4 bits for the opcodes that we need for this specific example because we want to add 2 numbers and then save them on the memory. And the rest are the addresses. And this is the word for the data, which is we've got 15 bits for the data and 1 bit for the sign. So I'm going to use, again, PC, MAR, IR, MBR, and AC. These are the registers that actually help us to circulate the data between different components of this machine. So as I said, there is only single line for a register. So I create a table for a register PC, MAR, MBR, IR, and AC. You need to know what each register does. It's important. And this is my memory. And as I said, the program counter is set to 300. It means that we've got to start reading from 300. So because of that, I only picked the memory from location 300 onwards. So let's see what our program is. So you write a program. This is your program because I said that program is set of instructions. The first line of your program, let's say when it's compiled, the second line, the third line. So these are the instructions. It means that the first 4 bits are the opcode. Look, guys, I use hexadecimal here because it's easier for me to represent the numbers. But if you wanted to use binary, instead of 2, you should put 0010. Instead of 9, 1001, 4, 0100, and 10001. Just for simplicity, I use hexadecimal here. So the first 4 bits, which I represent them by only one number here because I'm using hexadecimal, that we discussed in week 1. So the first 4 bits or the first number here shows the opcode. We've got the opcode list. There you go, 1 to 5. 1 is loading, 2 is storing, and 5 is adding. There you go, we've got this. And the rest is addresses. So imagine now we want to start. Program counter is set to 300. And now we are in step 0 and we are in the fetching cycle. Fetch means reading. So computer starts. Program counter at the first place, as you see here, send the instruction to be fetched to MAR. Send it to the MAR. Memory address register gets the instruction. Memory address register is a register which goes to the main memory and specifies the address. The address which is here is 300. It means that memory address register will go to the main memory to the address 300. And what it does, it brings whatever in the main memory as an instruction, brings it back to the MBR. Look here. MAR goes to the main memory and brings whatever it is to the MBR. Now MBR should send it to IR and MAR. Let's see. So program counter gives the instruction, program counter gives the address to the MAR. MAR is the register which go to the memory based on the address, gets the instruction, brings it back to the MBR. There you go, 1940 in MBR. Now still we are reading, we are in fetch cycle. Now it's time to pass it to the IR. Instruction register, here, actually I have both of them here, opcode and address, both of them are in one place. So the first bit we are reading. The first bit is the opcode, the rest is the address. First 4 bits is the opcode, the rest is the address. Now we want to understand what it is. It means that we want to perform the instruction. So we go to the execute cycle. Look, from fetch to the execute, we start understanding what opcode is and what address is. And also, as you see, the program counter at the beginning of execution actually is incremented. It means that make the machine ready for the next instruction to be fetched after execution. It means that the program counter is ready to give the address to MAR when the current cycle of execute finishes. So IR, in opcode, we've got to see look at the list. 1 means load AC from memory. From memory, which address? I showed you here. There you go. This is opcode. The rest is addresses that I showed them by 3 numbers because I said that I'm using hexadecimal. If you are here. So which address? 940. 940 is here. What? We've got to load AC. Load AC with this instruction. Load AC with what? With the number that we have here. What is this number? 3. There you go. We loaded AC by the from the memory from here. Now the execution finishes because we actually executed the first instruction. Now we've got to go to the next. Program counter is already ready for the next instruction. So it sends the instruction, sends the address to the MAR. MAR now is 301. It goes to the MAR memory address register, goes to 301, gets the instruction 5941, brings it to the MBR. MBR passes it to the IR. Look, this is the second cycle of fetching. In the second cycle, we getting the address from the program counter. MAR gets that, goes to the main memory by the address, brings the instruction to the MBR. MBR sends it to IR. Now we want to understand what it is. We want to perform that. If you want to go to the next cycle of the execute, you've got to increment the program counter. There you go. Program counter is incremented and we are ready to understand what it is. The opcode is 5 based on this instruction. We look at the opcode list. Opcode is add to AC from memory. Add to AC from memory from which part of the memory? From this address 941. So this is the address, this is the value that we have in 941. So what we've got to add. Now what we want to do, we've got to use adder or ALU because we want to add. Now we send a signal to the ALU that ALU, get ready, 2 numbers should be added. The first one, which is available on the AC, is 3. So AC is loaded to adder subtractor. The other one actually is loaded to the adder subtractor and we get the answer. There you go. This is the adder subtractor that we built in the first teaching block. This is full adders. This is 8-bit. For that, I should have actually 16-bit, but because it's easier for me to show here, I used 8-bit, but there is no difference in terms of the answer that I get. The first number is 2, as you see here. The second number is 3, 1, 1. This is 0, 1. If you add them, this is off. It means that I'm adding them. What I get, 3 plus 2 is 5, 1, 0, 1, 5. Excellent. Now, what happens is that 3 plus 2 is 5. I've got to update, add to AC from memory. So this 5 goes and sit in AC. This is the second cycle of execute. Now we've got to go to next fetch. Program counter is already incremented 302. So 302, program counter gives the address to MAR. MAR specifies address, go to the main memory, 302, gets the instruction, brings it to the MBR. MBR gives that to the IR. This is the end of the third fetch cycle. Now we've got to understand and perform what it is. So we've got to opcode this, I showed you before. 2 is what? Store AC to memory, right on the memory. Look, as soon as we go to the execute cycle, the program counter is incremented. Store AC to memory. So we've got to store whatever AC is on the memory. But on what place? On what address? On 941. So store AC to memory 941. So what happens? We've got to execute that. We've got to write this 005 on 002. You've got to write it, rewrite it on the memory. Here should go there. There you go. I wrote that to main memory. So now you've got to go for the next actually line, next instruction. But for example, you could have a break in your code and stop it here. So it would be a hold, stop, and you exit from the program. But now, as I showed you, you got the first number, 2, second number, 3, you added together, and we got 5. So guys, as you see here, I used all different components of, there you go. I used MAR to specify the address. I use IR. Actually, IR and MAR, I showed them together in execute because it would be easier in terms of showing. I use program counter. I use MAR and I use AC, and I showed you how we've got to use them. You've got to watch this video a couple of times. Do that yourself. Get a pen and pencil and do it yourself and see how it's going to be. So again, in one picture, in very short form, these are the step 1, 2, 3, 4, 5, and 6. All these 3 fetch cycles and 3 execute cycles. 16-bit word were used. 4 bits opcode was used, and program counter started from 300, as you see here. So again, chapter 2 and 3, it's quite important if you want to read the reference textbook. It's already on the Moodle page. Please watch this video. And also, there is a very good exercise similar to what I did on the worksheet. This week, on the practical session, we go through that together and we practice how we can see this fetch and execute cycle. Thank you very much. See you later.